Welcome to the Hidden Voltaic Village and the Land of Lightning. We are here to connect with the villagers and learn the three-part technique called the Voltage Seal Jitsu. The first part is understanding the construction, operation, and notation of the Voltaic cell. To demonstrate the strong relations between the two villages, we are taught by the Honorable 4th Raikage himself, the leader of the village. The Raikage tells us the Voltaic cells rely on the fact that redox reactions are happening spontaneously. For example, when you immerse a zinc strip, as we see here, in a solution containing copper ions, which is going to be Cu2+, something interesting happens. The blue color of solution is going to fade, and a brown-black layer of copper metal forms on the zinc strip spontaneously. Why? Because this spontaneous reaction involves the reduction of copper ions to solid copper and the oxidation of zinc metal to zinc ions. So, as the zinc metal is losing electrons or being oxidized, the copper metal gains electrons and becomes reduced, therefore creating the black and brown solid or layer of copper metal that is forming on the zinc. What we also notice here is that the mass of the zinc is also decreasing. Why is it decreasing? Because the zinc ions are losing electrons. Why is the copper mass here increasing? Because the copper ions are gaining electrons and, of course, forming a solid. We also can see that written here in two half reactions. We have copper gaining electrons to form the copper solid, which is reduction, and we have zinc losing electrons to form the zinc 2+ ions, which is oxidation. And the zinc 2+ ions that are formed are going to be colorless, and the copper solid is that black and brown layer that you see here. Okay, folks? In other words, zinc and copper ions are interacting in this beaker here, resulting in a reaction where zinc is going to lose electrons, which is oxidation, and copper ions are going to gain electrons, which is reduction. So that is what we're seeing represented here. Now, although electrons are being transferred, electrical energy is not generated because the reacting substances are in the same exact beaker. The Raikage continues and states, when we physically separate the half reactions, meaning the oxidation and reduction reactions, and connect them by an external circuit, the electrons lost by zinc then will produce an electrical current as they travel through the circuit toward the copper ions that gain them. And we can visualize that here. We have two beakers now. We have a solution that's going to have our zinc ion or the oxidation reaction. We have another beaker that's going to have our copper ions or the reduction reaction here. And so because they're separated, they have the ability to now produce that electrical energy or voltage, as we'll see as we go along. And this information provides the basics of any voltaic cell, that you must have two separate half reactions. And instead of simply just calling them half reactions, we simply say half cells, because the half reactions are separated into two individual containers, and we can say that these are our individual cells. Okay, folks? So sometimes you'll see half reactions, sometimes you'll see half cells. The Raikage then states that he will break our voltaic cell understanding into three parts. 1, construction of voltaic cell. 2, operation of a voltaic cell. And 3, notation of a voltaic cell. So let's get to construction. To construct a voltaic cell, you will need to make sure that each half reaction takes place in its own half cell. Okay, folks? So that the reactions are physically separated. That means we're going to have our oxidation reaction in one half cell, and we're going to have our reduction reaction in another half cell, folks. Next, you want to make sure that each half cell consists of an electrode and an electrolyte solution. So the electrode here is going to be the zinc bar, and the electrode here is going to be the copper bar. This is the electrolyte solution that has the zinc 2+ ions, and this is the copper solution that has copper 2+ ions. And then finally, we have to make sure that the half cells are connected by an external circuit that consists of three parts. So first, you have to make sure you have the wire. So we see our wire here. And then you want to make sure you have a voltmeter. And then you want to make sure you have a salt bridge. So the wire is going to usually have a switch that opens and closes the circuit. So we normally see everything closed here, right? Here's a visual of this wire being open, or the circuit being open itself. When the circuit is open, the electrochemical cell is inactive. When the circuit is going to be closed, then the electrochemical cell is active, because it has the ability for the electrons to move from zinc 2+ ions all the way to copper solid, which is what we're looking for in our overall reaction. Next, we have a voltmeter, which is going to measure the voltage generated. And so the voltage is generated based on these electrodes. So we have our zinc electrode and our copper electrode. And as the electrons are moving from the zinc electrode to the copper electrode, there's going to be an electrical potential difference between these two electrodes. And that causes a voltage. And so you'll see a readout of the voltage, say 1.5 volts or 2.34 volts, et cetera, et cetera. Okay, folks? And then we're going to have a salt bridge. And that's going to basically serve as a liquid wire, kind of enabling ion flow between the half cells to maintain electrical neutrality and complete the circuit in a voltaic cell. That means you need the wire, you need the voltmeter, and you need the salt bridge to have an overall external circuit. Without one of these portions, then of course you will not have an active electrochemical cell. When you have your half cells, electrodes, electrolyte solutions, and your external circuit in all its components, then electrons will move from left to right through the internal circuit from anode to cathode. So when we talk about electrodes, okay, what are our versions of electrodes? We have the anode, which is where oxidation is going to take place. And then we also have the cathode, which is where reduction is going to take place. Of course, we're going to get into more details as we go along. Now, the Raikage then speaks on the operation of the voltaic cell based on what we know from its construction, meaning why can this cell work based on how it actually looks or is constructed. Well, first, we have oxidation, which we know is going to be loss of electrodes that occurs at the anode. Therefore, this is our source of electrons here, folks. This is getting the process started. So we're starting with the zinc solid, and this zinc solid is going to lose electrons. As zinc loses electrons, it's going to form a zinc 2 plus, and those electrons that they lose, those 2 electrons, are now have the ability to move through the wire. Here is a half reaction to show that process. We have zinc solid going to zinc 2 plus aqueous plus 2 electrons. Again, the electrons are on the product side, verifying this is an oxidation reaction. Now, over time, the zinc anode is going to decrease in mass, meaning over time, as this zinc continues to lose electrons, it's going to continue to be used up, and used up, and used up as it goes along, right? Therefore, the zinc 2 plus concentration in the electrolyte solution will increase. So overall, the concentration of our zinc 2 plus will increase when you're in the oxidation or anode half cell. There is a visual representation of that zinc solid decreasing. So of course there was a longer piece of zinc here, and as you can see, it looks like it's chipped away because it is losing mass as it forms its zinc 2 plus ions, and therefore the zinc 2 plus ion concentration will increase. Great. Now we have to look at the reduction side, or the gain of electrons that occurs at the cathode. So reduction is going to occur at the cathode. We know we can think of red cat. For anode, we can think of an ox, right? Some kind of like little reviews from before. But at the overall cathode, this is where the electrons are going to be used up. So those 2 electrons are still moving, and they're going to be used up. How is that going to work? Well, our copper 2 plus ions, aqueous, that are in solution are going to, of course, gain those 2 electrons to form copper solid. So this copper 2 plus is going to gain 2 electrons to form copper solid. So you're going to get a lot more copper solid forming on this overall cathode, which we can visually represent here. As you can see, we had another piece of copper, and this is all the added copper around it. Therefore, over time, the concentration of our Cu2 plus is going to decrease, right? Because it's going to continue to accept electrons and be used up. And the mass of our copper cathode is going to increase. So we see that here. It's literally the opposite of what we saw with the anode in our zinc electrode. After several hours, the zinc anode is going to weigh less than the copper cathode weighs. And you can actually, of course, demonstrate that half reaction here. And when you add these 2 half reactions together and get rid of those 2 electrons, you also can write the overall cell reaction, which is going to be our zinc solid plus copper 2 plus aqueous, which is going to form zinc 2 plus aqueous and copper solid. All right, so the anode is going to produce electrons by the oxidation of zinc solid, and therefore the anode is the negative electrode in the voltaic cell. That's why we see it has a negative here, okay, folks? And then electrons are going to flow through the external wire from the anode to the cathode, where they are used to reduce Cu2 plus ions. So these Cu2 plus ions are going to be reduced to form copper solid. Therefore, the cathode is a positive electrode in the overall voltaic cell. Now, to maintain neutrality, a salt bridge acts as a liquid wire. But the question now becomes, how does it work? Let's get into it. So the Raikage states that Voltaic cells need a complete circuit to operate. And it's the salt bridge that completes the electrical circuit and allows ions to flow through both the half cells, acting as a liquid wire. And a salt bridge contains an inverted U-tube. So here's what a U-tube looks like. And if we invert it, it's upside down, exactly as what you see here as a salt bridge. And this inverted U-tube is going to contain non-reacting cations and anions dissolved in a gel. So for this overall Voltaic cell, the non-reacting cations and anions are Na plus and SO4 2 minus. As the zinc solid is oxidized at the anode, we know that the zinc 2 plus ions are formed and enter the solution, or the anode compartment, right? Therefore, SO4 2 minus anions from the salt bridge are going to move into the electrolyte solution to compensate for the added positive charge. Same thing over here with the cathode. We know that as Cu2 plus ions are going to leave the solution to be reduced at the cathode, Na plus positive ions are going to move from the salt bridge into the electrolyte solution to compensate for the missing positive charge. So ions diffuse in and out of the half cells, and then ions in the salt bridge are going to prevent charge imbalances and thus maintain electrical neutrality and complete the circuit, which is why it's so important along with the wire and the voltmeter itself. So we need, again, half cells, electrolyte solutions, electrodes or anode and cathode. We need a salt bridge, a wire, and of course the voltmeter. Now what happens if there is no salt bridge? Well, in a voltaic cell, the wire is going to conduct electrons, but the voltage is a result of chemical reactions at the anode and cathode that create a potential difference that of course drives the flow of electrons in the external circuit. Without the salt bridge though, electron loss in the oxidation half cell may create a positive charge. Why? Because as the zinc is going to continually create the zinc 2 plus, we know that this concentration is going to increase. And if there is no salt bridge, then of course there's not going to be anything to compensate for that increase in positive charge. So therefore the overall solution will be positive. Same thing if we're talking about the ion departure in the reduction of the half cell with copper here. We know that this copper 2 plus concentration is going to decrease as we create copper solid. So of course, that means we're going to be left with negative anions in solution, causing this entire solution to be negative because there's no sodium to compensate for the missing positive charge here. Having a specific positive and a specific negative charge is going to disrupt the chemical reaction and prevent the generation of a voltage. This means that this entire electrochemical cell will be considered inactive, okay? And that means the voltaic cell will not produce the desired voltage, folks. So the salt bridge is essential for maintaining charge neutrality and allowing the voltaic cell to operate effectively. The Raikage then ends with more details about the electrodes. He tells us there are actually two types of electrodes, active electrodes and inactive electrodes. So an active electrode is an active component in its half cell, and it usually is a reactant or product in the overall reaction. So for us, we've been talking about our zinc anode and our copper cathode, right? These are both active electrodes because they're actually actively solids within the overall cell reaction. So we see the zinc solid here, we see the copper solid here, we see that they're part of the overall cell reaction. We know that during operation, zinc's bar mass is going to decrease and the copper 2 plus ions are going to plate out onto the copper ball and cause that copper bar to increase in mass as well. Okay, folks? And of course, we have our half reactions to demonstrate that we're using those actual solids. An inactive electrode is going to provide a surface for the reaction and completes the circuit, but it does not participate actively in the overall reaction, meaning you're not going to find the inactive electrode in the overall reaction. It's just there to help complete the circuit and again, help with the overall reaction here. Inactive electrodes are necessary when none of the reaction components can be used as an electrode, okay? And a lot of times when you're thinking of inactive electrodes, there are usually going to be two of them that we focus on that are unreactive substances, and that's going to be our carbon in the form of graphite and platinum. These are the two inactive electrodes that we usually see in our course, okay? Here's an example of a voltaic cell using carbon or graphite as an inactive electrode in order for this overall redox reaction to occur. Okay, so we have iodide and permanganate. So we have our oxidation half reaction of iodide here and the reduction of our permanganate here. And then we're going to have the graphite electrodes here. They're still going to be connected to a wire. There's still a salt bridge. There's still a voltmeter. Our salt bridge this time, though, is going to be K plus and NO3 minus. And when we're looking at the overall reaction, there is nothing that shows graphite because, again, it's inactive. It's not actively part of the reaction. What is it actually used for then? As you can see, the carbon graphite here is used to oxidize the 2I minus. When the 2I minus is oxidized, it's going to form I2 solid that has the ability to plate onto the graphite electrode here, or anode. Then in the reduction half reaction, we have our permanganate plus 8H plus, okay, and it's going to accept 5 electrons that are coming from the anode side, right, and as we can see, and it's going to form Mn2 plus aqueous and water in solution. So we're actively not using it here, but it is a part of making sure the electrons are moving to this half cell. Okay, folks? So of course, we will be able to see active and inactive electrodes throughout. Now, the Raikage wants us to review our diagram of a voltaic cell, just to make sure we're getting all the details. And of course, making sure that you're using your flashcard moments. So of course, we know we have different components. We have to have 2 half cells here. They have to have electrodes. One electrode is going to be an anode that's on the left. The other electrode is a cathode that's on the right. The anode is going to represent oxidation. The cathode is going to represent reduction. We also know we're going to have electrolyte solutions here. We also know we must have, each half cell also must have its own half cell reaction, right? Or half reaction here. So we have the oxidation half reaction here. We have the reduction half reaction. We can bring these together to get the overall cell reaction as long as the electrons that are moving are equal, right? We also have our wire, our voltmeter, and our salt bridge, which represents our external circuit. That's going to allow the direction of electron flow to go from left, or the anode, to the right, or the cathode. Okay, folks, and we can see that demonstrated here with the little electrons that are going from one side to the next. Moreover, the Raikage tells us there's actually a useful way to describe those same components of a voltaic cell, and that is cell notation. So when you're trying to write a voltaic cell out, then the components of each half cell are written in the same order as their half reaction. So therefore, you're going to be starting off with the anode or the oxidation, and then you're going to have your salt bridge, and then you're going to end with the cathode or reduction. Another way of saying that is that all the anode components are written on the left, and all the cathode components are written on the right. There's going to be a single line that shows a phase boundary. So, for example, if I'm showing zinc solid here, and I'm showing zinc 2 plus aqueous here, there's going to be a single line that's going to represent the separation between these phases. Same thing here, copper 2 plus aqueous, and then we have copper solid. Next, you can write a double line to represent the half cells are being physically separated by a salt bridge. So let's go ahead and write that down quickly. All right, what are the components of the oxidation half reaction or the anode side? Well, we have zinc solid and we have zinc 2 plus aqueous. We know in order to show, as far as cell notation, that entire anode side, all we have to do is write zinc, the state of matter, and then a single line to distinguish between the 2 phases of matter here. We then write a double line to represent the salt bridge, and then we write the components of reduction, which we know are going to be our Cu2 plus, which is going to gain electrons, and then our Cu solid. We have to write a line to show changes or a difference in phase change, so aqueous versus solid here. Okay, folks? And that is actually the cell notation for this diagram. You see how much faster it is to write out when you actually have the cell notation? This automatically tells me that I have a salt bridge, that I have the zinc that is going to give up electrons and form this ion, and that I have this copper that's going to accept those ions and form this solid, all from this one single notation. You can even go further and write concentrations. If concentrations are not given, then we say, of course, everything is going to be 1 molar here. So instead of aqueous, sometimes you can see it written as aqueous 1 molar, or over here, it'll be aqueous 1 molar as well. Okay, folks? If you had to have concentration. Sometimes, of course, they can put 2.5 molar, whatever the molarity is for that particular ion, for example. And it has to be the dissolved components that you're going to get concentrations for, right? Not the solid portion. We also can do this with the inert or inactive electrodes, right? That we talked about before. So let's go ahead and write the cell notation for this particular voltaic cell that's using the electrodes that are inactive, okay? Again, we're focused on making sure we start with the anode or oxidation information. all I see here is I minus and I2. So that means I'm going to have I minus, which is going to be aqueous. And that I minus is going to lose electrons to form I2, which is going to be solid. Great. We still have our salt bridge here. And now we have a bunch of different ions. And so it's a little bit different for us, right? But even before I continue on, am I missing something here? Yes, I am. You must make sure that you're adding in the actual inactive electrode, because otherwise we don't know where this I2 is going to be plating on. So I would actually rewrite this here as graphite first to show that inactive electrode, a line, because the graphite is a different phase than the I minus aqueous, right? So I'm going to have my graphite, a line, I minus aqueous, and then it's going to be the same after that. Another line, I2 solid, and then we're going to have our salt bridge, which is 2 line. All right. Then, of course, for everything else, we have to make sure that we are using all of the actual ions that are left over. Where am I getting this information from? Straight from the half reaction. So we have I minus, we have I2, we see our electrode. Over here, this reduction half reaction is going to be MnO4 minus and H plus. All right. And then we also are going to have Mn2 plus aqueous. Of course, for the electrons in water, we don't have to write those down. So I'm going to write all of my ions here, and then of course graphite to show that we still have the inert electrons. Let me go ahead and write those. All right, from my half reaction, I'm going to start with the MnO4 minus aqueous here. Okay. And then because everything is in the same state of matter, they're all aqueous, I'm just going to write a comma in between things that are the same state of matter. So MnO4 minus aqueous, then I have my H plus aqueous, comma. I'm not going to be writing electrons. Then I have Mn2 plus aqueous, which I have here. Okay, don't have to write water. And then, of course, I have my inert electrode, which is going to be graphite. So because aqueous and the graphite are 2 different phases, I do have a line that I have to write there. And that would be the notation for this voltaic cell. So as you can see, just like the Raikage has told us, cell notation makes it way faster for us to be able to understand all the components of those particular voltaic cells just by writing these one lines. The goal is that we, of course, are making sure that we are using the chemical reactions that are given, or sometimes you may not be given a chemical reaction. You may be given half reactions and have to figure out the overall reaction, or you may be given an overall reaction and have to figure out the half reactions in order to be able to figure out what's the anode or cathode, be able to figure out what's being oxidized or reduced, for example. So it really does depend on the question, but the Raikage is going to allow us to use their training grounds for an example. So let's go ahead and get to it, folks.